Hello friends, welcome you all to the session 27 of form-based development. Okay, we are going to take a different topic today and maybe subsequent two lectures. It's all about how memory is managed. Okay, we saw memory hierarchy and cache memory organization in detail so far. Now we are going to see two important functionalities, okay, related to memory. One is memory protection, other one is the virtual memory. Okay, so let us worry about virtual memory and MMU later. Today's focus will be on memory protection units. Okay, let us see what it is. So in this discussion we will be covering about a little bit. I'll give a overview of process and context, which though I have touched upon this in subsequent earlier classes, it is appropriate to just talk about it a little bit before we get into processes and memory protection. So then we will talk about what are protected systems and why do we need a system which has got protection built into it, and then we will go into the detail of MPU. Okay, and then we will see how MPU can be configured. Now just to give you a overview, okay, let me choose a nice color. See, we saw ARM processor, then we touched upon coprocessors, okay, and then we saw memory hierarchy, and then some memory controller. This is main memory, which I am assuming to be outside of the SOC, and memory controller connecting to that, and then we have address bus going there, and the data bus is coming to the coprocessor. Here what we are saying is what VFC. Okay, an example. So and then yesterday or the previous classes we talked about cache, which came in between the memory controller and memory. Now we have two topics to discuss. One is memory protection unit and memory management unit. Now this is not the focus now, this is the focus, memory protection unit. So one thing that you should remember is memory protection unit functionalities are built into the MMU if MMU present in the system. Okay, so there won't be a system with both MPU and MMU as a separate entities. This functionality will be absorbed by MMU, and MMU is actually having a MPU functionality also built into it. So if I say that system has an MMU, that means you can implicitly assume MPU functionalities are there. I have not told what is the functionality of MPU, but this difference you should remember. Now because in our discussion today we are going to talk about memory protection unit, the MMU is not there. Okay, let me remove right now for a moment cache also to just no, MPU is there. Okay, only MPU. That means there is no MMU. In that case, what happens is the address bus that goes into the MPU is also going into the memory. Okay, this is address bus. Okay, because there is no logical memory or physical memory, virtual memory, those concepts are not there when we are talking about MPU as an independent unit in the system. Okay, Again, an option of having an MPU or MMU is a designer's choice. Okay, so if the system what you build, okay, does not need virtual memory support, but it needs the memory protection unit support only, then the choice will be to take only this module and do not bring in the virtual memory at all. In that case, what happens? The memory addresses what the processor gives out is directly going to the memory, okay, and accessing that. So the physical memory is what processor sees, okay. Processor or any processors running in the processor does not have any other virtual memory system in its execution. So whatever is the memory, it sees is the memory management, the main memories area. So if suppose if it has got only 256 MB of main memory, then the program space also will be only limited to this. So we may have to write everything only considering that there is only a 256 MB of space in the system, and all the programs should fall within that. Whatever we are deciding about code or data or stack, where it should go, it should all be restricted to only the physical memory available in the system. There is no MMU to transfer it to another unit, so that the virtual memory space may be bigger and the actual physical memory what you have in the system will be smaller. So that option is not there. So we have to keep in mind that when we are talking about only MPU in isolation, we do not have a MMU present in the system, and there is no virtual memory concept here. Okay, so we can build a system like that also. Now you may wonder who is providing this MPU and MMU. Whatever I am discussing now is all provided by ARM. See, ARM does not only give you IP of the processor core. Okay, it also gives, as we saw, a cache controller and a cache core which you can build and configure using the controller, and it also provides coprocessor and VFP, and it also has a bus standard which I will be talking about in subsequent classes. So it also provides you the necessary IP along with all the text for testing purpose. Also it gives you so many support in the while providing IPs also. So bus is there. It provides all the main ingredients for building your SOC. So MPU is also one of the coprocessors. Okay. Now when I say MPU is a coprocessor, okay, you may immediately remember me saying that the coprocessor will not have access to the address bus, right? I mentioned it earlier. Let me clarify what I meant by that. Okay, maybe this color is better. See, in case of functionality, when we want to build in a new functionality, we want to add. We have talked about vector floating point processor, which is the coprocessor. It needed some access to memory also because it has to keep its data here, and then it will be doing a floating point arithmetic. During that time I said that ARM only manages the memory space and it will only generate the and MMU also, they are all coprocessors. Okay, but the number is 15. It is specific to coprocessor 15. Whereas here I said that it is 10 and 11, if I remember correctly. So this coprocessor 15 is reserved for MPU, MMU, and cache controller also. So but I am also saying that MPU is connected to the address bus. But in the VSP case, it was not connected to address bus, but only to the data bus. Whereas in case of MPU or MMU, they need to be connected to address bus because they have something to do with the transfer of translation of the address, that is MMU's job. Okay, I will talk about that later. But MPU's job is to protect the memory accesses. Okay, different area of memory it wants to protect it. So that is the functionality of MPU, which I will go into detail now. So if it has to perform a job of protecting the memory accesses, it should know what the ARM processor is accessing. Okay, so as I mentioned earlier, the address generation is with the ARM processor. Nobody is going to control that because our instructions which are getting executed in the ARM processor only controls how the addresses are generated by the processor. But the generated addresses can be seen by the MPU or for that matter MMU, and then they can read it and do some translation, and then the circuitry can be such a way that that MMU means it will translate the address will be connected to main memory. In this case, the same address bus goes to main memory, but MPU also looks at the addresses. Okay. So, and is it required that it needs to be connected to the data bus? Of course, yes, because the MPU's controller are configured through the coprocessor instructions. Okay, so it may have to transfer some data. That coprocessor instructions should be transferring the content from the register here to the some controller here and from here to here. So this MPU and MMU are connected to both address and data buses, and they may view the they may read the content based on what is happening, which instruction is getting executed by the coprocessor. If suppose ARM processor is executing a coprocessor instruction which is saying it is 15, then MMU or MPU which is there in the system will become active and then try to understand what is that being asked by ARM. Okay, so this is how the whole thing works in the case of MMU. Let us come back. Okay, so let me change the color. So I think that overview has made you understand that it is not compulsory that coprocessor cannot look at the data bus, but if it is needed, it can be connected to both address and data bus. Okay, and driving the data bus is controlled. If the coprocessor has to drive the data bus, that means it has to write into something, into the memory or back into the register, something has to be transferred, then that will be controlled by ARM. So ARM will control what the coprocessor will do. Okay, but it can be seen sitting on both address and data bus too, based on the functionality of the coprocessor. Okay, in the case of DFP, there was no need for it to know the address, what is happening, because it was interested only in knowing the instructions, so it was looking at it. Okay, but there is no restriction that it cannot be connected or something. Okay, that's you have it in your mind, so that when you look at the functionality of different coprocessors, you will know that. Okay, let us see what are the processors. Okay, these processors are something which is running in the processor. Okay, different context is maintained by the processor. So if there is a single processor in the system, okay, I am not talking about multi-processor system, it is only a single processor, then there can be only one process in the processor. Okay, only one process can be active at a time. Just remember the word active. Only one process can be running at a time, but it can support multiple processors. So if it has to support, the processor has to support multiple processes running, then there should be some software functionality added to the system. Okay, it could be a OS, or maybe we can have some other control system, minimum scheduling system, and minimum process creation and process switching. All that, if it is there, then it can be done. Let us assume for simplicity sake, a small kernel, microkernel maybe, is in the system which is getting the control first, and then it builds a set of processes in the system. Okay, so this is the main memory. Maybe all the processes will be in the memory, but only one will be executed. That means what? This process related code, data and stack will become active. So this part of the memory will become active, and then the processor will execute the process P1 now. After that, maybe I will tell you different reasons where this will go back, okay, and the new process will be loaded. So this is, you might have known this if you have undergone an operating system course, but I am not assuming that you have good understanding of this. Okay, without the intricate understanding of OS, but as long as you know that what the process mean and how a process can be run on a processor, that much of knowledge is enough to understand the different features that are provided by these MPUs and MMU and whatever I am going to discuss today and even in subsequent classes. Okay. So process is a program execution. The components of processes are the code to be executed, the program to be executed, the data the program uses while executing the code, okay, and the resources required by the program such as heap or stack. See, I am not maybe spoken about heap for a moment, for maybe in the beginning of the class something I have mentioned. Maybe let me tell you what a heap and stack means. This is okay. This is stack because going downward. Okay, this is some memory. Okay, in the main memory, this is a heap. So you might have come across, if you are written a C program, malloc. Okay, and this you would have come across this particular function call. That means it is getting some dynamically allocated memory. Okay, and then the program uses that memory which will be allocated from the stack, from the heap. And then what happens? It may release free the memory, and then it goes back to the heap, and then some other time and some other process or maybe same process. Okay, because this heap, it all depends on how it is maintained. It is maintained by the OS or by it is maintained at the process level. So in that case, what happens is the heap space will be given whenever it is required, and then the program uses it and releases it. So this kind of heap and stack normally is managed by OS. So they will also be there in the as a part of the resources for a process. And status of execution is maintained in the registers and the CPSR values. So when a process needs to be moved out of a processor, and then a new process has to come into the system, into the processor for execution, because I am talking about only single processor. Then what happens is all these things, okay, don't think that every time whole code is coming and sitting in the processor. No, because code will be residing in the memory, and then it is being accessed whenever it is needed. So instructions are executed, it is accessed. Similarly, data is also residing in the memory, and whenever it is needed, some data is accessed and something is written back. So they the whole chunk of the data code is residing in the main memory only. But pieces of that will come to the program processor and then get executed, and then based on the execution, the data moves between these two. So when I say during a process is saved, some state is maintained here in terms of register values or CPSR values. Those things need to be saved. Okay, so that may be a context, okay, which is maintained by the OS, and then for each process there will be a process ID, and then it maintains the particular context of a process in its own structure, and then it makes sure that one process goes out and another process comes in. So it will be very difficult to go into details of this because it will become another operating system course. So I am just starting with this. I presume that this much of introduction is enough for this particular course from this context of the course. Okay. So these are the contents are to be concerned with a particular process. So based on an event, okay, I'll tell you what are the events, possible events. OS may say a state of the active process and may restore the state of a new process. Where it says, it normally saves in the OS system area where it is maintaining the context of each of the processes in the system. Because only OS knows which process is running and which processes are residing in the memory as a background job, and then what state it is, all those things. Okay. Now, what is the context switch? That means a switching between one process to other. So what must get saved on a context switch? everything that the next process may damage. That means if it is going to be modified, then it is better to save them. So program counter will be changed by a new program which is coming into the PSW. The program status word will be as well as general purpose and any floating point register. So normally what happens with the floating point is we don't know. Suppose there are so many processes running in the system, P1, P2. Okay, the processor as such, no ARM processor does not know, or the OS running may not know whether a particular process, okay, is going to use the coprocessor or not. So normally what happens is only when a process needs the coprocessor or floating point processors by to be specific, then it may be having some coprocessor instruction in it, and that will be executed by the processor. So normally coprocessor is getting saved into the context only when a process wants it. Okay, it's not always, but you are sure that every process needs the registers in the processor ARM. So that has to be saved by default, but coprocessor may be saved only when it is needed. Okay, just keep in mind because I am mentioning here, I thought I will just touch upon that. So as well as memory and code needs to be, not that it is saving from the processor, it has to be so that needs to be taken care of. Okay, it cannot access anything else other than its own area. So that's where we need the functionality of MPU. Okay, you may wonder why I'm not coming to the MPU at all. I'm talking about process, context switch, and all that. The reason behind is that you should know the intent. Okay, we should know why we need an MPU before we start learning about what is inside. So it is needed when we have multiple processes running in the system, and multiple processes, they have their own code and data. So when a particular process is running, suppose P2 is occupying the seat here in the ARM processor, it should only restrict its accesses to the code and data of its own area, and it should not touch this. But can you guarantee that they do always access only this? If a proper process is there, it may. But if there is a implicit inadvertent mistake or maybe intentional access could happen. So in that case, what happens? It may intentionally try to access some other part of the memory. So during that time, there should be some provision that is supported by hardware to protect it from access from other processes. So that's what we are coming to. Okay, as well as some file access if that OS supports file management unit. Okay, file system. Okay, scheduling and context switch. So any process may give up the CPU. Okay, give up the CPU means it may willingly wants to go out of the CPU by performing an IO operation. When it does the IO operation, OS gets the control because all IO operations are managed by OS. Okay, why? I'll give you an example. Suppose process P is there and process P2 is there. Both of them are trying to output onto a serial port. Okay, call it as UART. Okay, this is a peripheral device, and you can write it into this, and then the characters will come out. And suppose you are connected it to a PC. Okay, PC is there. I'm showing the old CRT display. Okay, so if it is connected to the serial port, the data will come here. Now, suppose process P1 has put some hello world. Okay, and in between it gets scheduled out, and then P2 gets the control of ARM. Okay, ARM processor. Now P2 also tries to write into UART. So as you know, hello world could have been written into some buffer, and then the UART is trying to put it into the serial port. It will take its own sweet time because of the baud rate. So you get, if it is 9600 baud rate, it will take hell a lot of time compared to the execution speed. So the characters may be hello world, maybe hello has come, world has not come. Then P2 has D2 also is interested in sending some characters out, and it is writing maybe how are you. Now what will happen? Hello will come, then how are you will start coming, because it is directly accessing it, and it may correct the buffer, or it may stop this buffer from, it may overwrite it into it, so that whatever process P1 wanted, that may get overwritten. So we should not allow the processes to access the peripherals directly. There should be some controller, that is the OS, so that it can order the sequence of accesses. And suppose if it is busy with the previous one, it may hold the access of this, something like that. So there should be some protection. That OS will bring in that protection. So in that case, what happens is, when this is executed, OS gets the control, because it is waiting for a character to be entered by the processor, some user. This process may have to wait for long. So that time what happens, the OS may bring in another process to execute. So this may be one of the reasons for a new process to come into the processor. Maybe the process wants to wait for some event to happen, because some buffer to be very free. Or it may say that I want to sleep for 10 seconds. The process needs to wait for 10 seconds. That means what? A new process can come into the processor, so it will give up the CPU. Or it can wait for a device interrupt to happen. Maybe it has given a file access and then waiting for the file to be copied by the DMA to the memory before it can do any useful work. And it can terminate itself. They say that okay, exit, or it may execute something to kill itself. So in that case, the process will terminate by itself. So these are the reasons where a process may go out of the CPU and a new process may come into the CPU. And then other one is OS can possibly schedule it. So there are some scheduling mechanism where each process is given a time slate, okay, for each process to run. So OS may decide that okay, your time of 10 milliseconds or whatever is there over. So this has to go out, and then now new another process which is in the ready queue may come. So these kind of are priority. A new process with a higher priority has become ready. So whatever may be the state of the low priority, it should be thrown out, and then a new higher priority task should come out. Or a page fault, the current process has accessed something and page fault has happened. Okay, then also there are possibility of a new process coming. So when give up the CPU means what does mean? Switch the current process out and get another process in. That's what is the job of the OS. Okay, so this is a different scheduling concept. Just start. I will just give a high level overview of OS. Okay, now let us go into more detail what is required for us in the MPU. Now typically, if you assume it is a lower address and it is a higher address, okay, because we are assuming that lower addresses are having the system memory, okay, the system related code and data, and then even the interrupt vectors, okay, IVT interrupt vector table is also part of the system. So they are all residing in one part of the memory, okay, and then the user program will be running here. Okay, this is a typical scenario of how the layout of memory is used by an operating system living along with the user programs. Okay, so it could be that instead of one process, there are multiple processes. Job and task are process, but in our discussion they are same. Maybe if you go into the detail of particular OS, it may differ, but at this moment we are not bothered about those details. So different processors may be occupying different parts of the memory. Okay, that you should know. Okay, so the CPU is multiplexed among them. There is a single CPU sitting. Okay, CPU and the processor are interchanging with. What I mean by that is the ARM processor. Okay, core which is used by all of them, but in turn. One guy will use it, then the one job will go out and another job will come and it will be executed. When I say it is using means that job is getting executed. Okay, those instructions are getting executed by the processor, and then it will keep it here with the help of OS, of course, and then the new process will come in and then they will start running. Okay, so this is the context so that we understand the protection requirement. Now I am going into little more details. As I mentioned to you, our lower addresses are here. Okay, sometimes it is drawn like this, and then sometimes I put the lower address down and then write a higher address there. So you may get confused which is low and which is high. So I am just mentioning it for your clarity. Okay, let us change the color. I spent on blue for long. Okay, now what happens here? This is that OS. Okay, the structure is a scheduler actually. OS. Now there are multiple processes which are already in the system. Okay, who created the process? OS creates the processes, and they are all there. Now there are some access rights defined. So here you see a process A, when while executing, you know that it can execute a branch with the offset, right? Branch with offset, okay, or with the label, branch with link register, and then what happens? It is moving to another address. The instruction execution moves to another address, and then it starts executing from there. Now this address cannot be mapped to a, a location or an area of memory which is meant for other process. Well, okay, in the sense, if it is not allowed to execute, okay, especially execution may not be allowed, okay, but sharing of data is allowed. Okay, there are some ways we can share the data between multiple processors. So that time we may have a shared memory which is in the system, and we allow a process. Then in that case, this may not be a part of this process B, this area. It may be a shared memory between B and A. In that case, it may allow this access, but code access is not allowed. Okay, and some places maybe data access also may not be allowed, because process A and C, they don't have anything in common. They are not executing anything, for a particular common application. So they may not have to share any data between them. So it is not allowed. So that kind of a restriction may be there. Execution access restriction, or even data access restriction, and then maybe you may also have some kind of a part of the memory of OS, maybe data allocation, okay, may be accessed by the processor, because if it wants some support of the OS, it will do it through calling the system calls. Okay, that's why we call it a system call. So it may not access it directly, it will access the OS calls, which will allow the process to use some of the resources, semaphore, or even any locking mechanism, mutex, anything, any OS features can be accessed. So this way we have to protect the OS first of all from the rest of the processors, and then we have to protect each of the processors from other processors running in the system. So this all can be done with the support of the processor. That's what we are going to see now, how it is implemented. Now let us see what are the protected systems are. There are two things: shielding a system resources. When I say resources, means it could be memory or peripheral, and other tasks from unwanted access is called protection. Other tasks means the process area of the other task. From unwanted access is called protection. Now two methods are there. One is unprotected system. What I mean by unprotected means it relies solely on software to protect the system resources. Need to have cooperative tasks for reliable functioning. What I mean by that is, suppose I don't have MPU in the system, okay, because I don't have space in the SOC. This is a very small SOC. Okay, MPU also is a hardware, right? It accesses some part of the chip. So I don't want MPU. I have decided that I will not use the MPU in the system. I have built a SOC with the ARM processor. Okay, then there can be a possible that there are systems without an MPU, but still I can support multiple processors in it, provided they are all cooperative parts. What I mean by that is, they know what their limitations are, what their address limits are, and then they are all well written for that matter, and well tested, so that they don't access inadvertently into the other areas of the process. Okay, and there is no OS. Maybe OS is there because if multiple processes are there, a simple small microkernel may be there to create these processes, but we have to manage it. Okay, somehow. Without MPU is difficult. We have to have a reliable functioning of these processes to make this this system run reliably. Okay, but what the advantage we get? We get there is no overhead of MPU or overhead of protection and other limitations. No hardware limitations, hardware functionalities which are complex. They are not there in the system. But it has to be very cooperative task for a reliable functioning. Otherwise, they may disturb the normal functionality. Now, what is a protected system? Here, relies on both hardware and software to protect the system resource. Okay, I'll tell you why software is also needed, because as I told you, MPU needs to be configured first. Okay, configured in the sense it should be enabled. It should be configured which memory is having what access, which process has its own area, and which are the other processes running, what is their protection mechanism. All this needs to be programmed into the MPU. Who does it? Using the co-processor instruction, MRC and MCR, similar to cache. We exchange some contents into, from the co-processor register, and then from ARM register to co-processor. We write something into some register, and then this guy behaves perfectly. It starts functioning as it's expected to. It starts protecting the system. So prior to the MPU enabling, the system is open to anybody. Okay, so we need some software which runs at the beginning and then starts protecting different areas of memory, and then starts giving the control to the different processors. So the software is required to configure the MPU. Okay, that is, sometimes it is part of the, most of the time it is part of the OS job, but I am trying to tell you why both are needed. And dedicated hardware enforces resource ownership and restricted access. So it, who is the owner of a particular area of memory is controlled by the hardware. Okay, very good. So let us change color for. Okay, now protection hardware in ARM. Okay, what is the hardware? So ARM provides several processors equipped with hardware that actively protects system. One is MPU. I told you. MMU. I mentioned that. MMU includes MPU functionality. Okay. MPU provides hardware protection of several designated regions. So I told you different regions of processors are there. The different area of memory is called region. Okay. I'll explain you more about that. MMU provides protection and adds virtual memory capability. Okay, let us not bother about this now, because anyway we have the next question talking about that. Okay, now let us see an overview of what all systems have MPU in it. ARM CPUs, which are used in embedded systems with fixed or controlled application program, do not require a full MMU. Okay, so suppose if we decide this is the area of particular, physical memory is limited. Okay, and then the number of processes running is also limited, fixed. Okay, we are not going to dynamically create more processors and then try to look for space. So in that case, what we can do is, we can, in the memory, we can allocate some different locations of the memory for different processes, and then maybe we need MPU functionality so that the protection is done by hardware, and we can start executing this code. Multiple processes will be in the system and they will be reliably running as long as the number of processes are fixed and the area that they are going to use are also fixed, and these are all controlled application programs. Okay, that means it is not going to go in terms of size, in terms of its memory requirement, and then the functionalities are all well defined. So in this kind of scenario, we can do away with MMU. So for such system, a simpler MPU is adequate. CPUs, which are the CPUs, that is ARM CPUs, which use MPUs are this and this. Okay, let me give you a overview now. So these are all the advanced versions of ARM. Okay, and when I talk about the whole SoC, it is a CPU. If I talk about only the core, it is a processor. Okay, if you remember, so CPU is the bigger cousin. So these are all different cores inside the CPU. Now they may have number of regions. Most of them are 8. Okay, which are either can be configured separately as instruction and data, or the regions. The regions are memory regions, which can be configured separately as instruction region and data region, or they can't be. Okay, it's a common area for both instruction and data. Okay, no is there for this code, but there is one which is unique, which is 940, which has got 16 cores, but still the numbering of these regions are always 0 to 7. Okay, I will be talking about this, but there will be an instruction region which are varying from 0 to 7 and data regions which are varying to 0 to 7. So what I mean by region, a region is some part of the memory. Okay, so how many such regions I can have? 8 regions we can have in the ARM processor, and some can be identified that it is the instruction region, some can be identified as data region. So let us not worry about these things, because these numbers and things will, it's not the need, you can always look at the manual to understand them, or you don't need to look them up. Okay, so what you need to know is at a high level, some 940 has this support for both instruction and data that can be configured, and as a different two regions, and whereas these two will have a limited 0 to 7, 8 regions, but you can choose, okay, 0 region is for instruction and the rest of it for data region. We can configure it. Whereas here we cannot even identify a region is a data or instruction. They are only treated as a region, single region. Okay. Very good. Yeah, let us get into MPU. Okay. So two major classes of resources that need monitoring, that is memory systems and peripherals. I told you that memory and peripherals are mapped to the same. Peripherals are also memory mapped. Okay, that means the peripheral registers also accessed as a memory content. So LDM or STM or LDR or SDR are used to access them peripherals. So they are all mapping into some part of the memory. So we need protection for them also, or some attributes specifically meant for peripherals. So that can be achieved by using MPU. So peripherals in ARM-based systems generally memory map. I told you MPU uses the same method to protect both the type of resources. So it doesn't differentiate between these two. Instructions are same. Okay, and you can define a different attribute for each of the regions. Okay, I will tell you what are the attributes are, and we can different regions of the memory can be treated separately, differently. Okay. Okay, what is the region in MPU? An ARM MPU uses regions to support and manage system protection. A region is a set of attributes. Still, I have not told you. Wait a minute. Processor code holds these attributes in several CP15 registers. So some attributes are there for each region. Okay, some memory, part of the memory. There is another part of the memory. They are different part of the memory, and they have different attributes. So these are all maintained in the CP15. CP15 is what? Coprocessor 15 register. So the MPU, as I mentioned, is implemented as a coprocessor in the ARM system. So identifies each region by a number, okay, which ranges between 0 and 7. So I told you there are 8 regions. So the numbers are there which are varying from 0 to 7, and regions are independent of whether the core has a 1mm or forward architecture. So this is whether it treats data and instruction memory as separate or unified single memory, doesn't matter. The regions are same for both. Okay, the way it handles are same. Now let us talk about attributes. Following are the set of attributes. The region is defined by a starting address and a length. Let me change color. See, every region is, again, you have to remember that it is a part, the memory area. It is nothing but a memory area. So if I need to identify a particular part of the memory, so suppose it is 0 and this address is maybe some 20,000 hexadecimal. Okay, this is some 30,000. So like that, I am identifying different areas in the memory. Now you have to mention what is the start address and then what is the length, okay, length or size, whatever you call. So these two will exactly tell you what is the start address of the region and what is the end address of the region. Once you are adding to these two parameters, you can find out. So we need this. Region is defined by that. Access permission could be any of this. That means a particular area in the memory can be both read and write. What I mean by that, if a processor, okay, is executing an instruction, when will the read or write will happen? Only when it is doing some LDM, LDR or SDR, okay, SDR, LDR, but all the load instructions or store instructions. So especially for a data, okay, and for a code area, it is the instruction. So anyway, there is no read write for a code area. So first of all, code area, okay, has to be read only. Okay, hardly you find a reason for it to be a read write, right? This is understood. Now data area, there are two possibilities of data area. One could be that I want a constant location. Okay, I store all the constants in the program. Const, you might have seen it in the C program. So I want to keep all the consts here. That means what? This data area which is maintaining constant values to not be written by even our own program. The program, say, suppose process 1 is having the owning this address, okay, its own range. Okay, we assume that P1 is having this code also, but that doesn't mean that the process can write it into its own code area, right? It can read from it, but it can't write into the code area. Similarly, it cannot write into some part of the data area because it is a constant. So we don't want runtime this area is modified. We don't want this to be modified. So that way we can say that as a particular data area is read only. And then some area we want the data to be written and read and written. So it can be read write. Okay, but you may say that some other area is, which is not in its own purview, is a P2, it should be have a no access. So we need access permissions which are one of this. There is no read, permission like write only. Okay, please remember, it cannot be. If you want to write, you have to read that location first to write. So or there won't be any need for only write only access to a particular part of the memory. Okay, so normally it is not supported, so we don't see that. Okay, and then a cache policy. See, though when I spoke about cache, I only talk about cache there, but suddenly when I am talking about MPU, cache is coming because cache can be there without an MMU. Okay, cache can be here, and then the address may go here as well as it will go to this guy. Okay, and then it will go to memory. Okay, so sorry. Okay, so it is not that while MPU is there, cache cannot be there. Cache can very well be there. Only MMU is it cannot be there. So cache can be there. In that case, what happens? We need to have some features, attributes which are related to cache. Why? We are talking about memory attributes. Okay, so we can associate some part of the memory, a region, whether it can be cached, okay, or whether it can be a write through policy or write back policy. Okay, there's kind of a different properties can be there for a particular region of memory if the system supports cache also. So because we are talking about memory might have, this system may have a cache, so we need to have a feature supported in the MPU so that if the cache present, then we can assume we can configure the MPU so that cache is also, behavior is also managed. That is very important to have in mind. And then similarly, write buffer can be there. It can be, as I told you, it's a PIPO which writes into the memory. Okay, write buffer. We talk about it in detail. So if there is a write buffer, whether whether it can go through a buffer or not. That's a decision which you can defer. Controlled access based on processor mode. This is another thing which I have not told you. An ARM processor, as you remember, it has got a user mode, then supervisor mode, system mode, user mode or system mode, and then there are FIQ, IRQ, aborts, all that we saw. And if you remember, recall, okay, these are all supervisor mode, okay, with its own bank register, okay, and then system mode has it's also part of supervisor mode, okay, but it uses the same register set as user mode. So there are some control pins coming out of the processor which will give you indication of NOPCIC. Then it will give you indication of whether it is in the supervisor mode or user mode. So some protection can be given, some privileges can be given based on the mode. This is very important because normally OS will be running in the supervisor mode, okay, and then all the user programs will be running in user mode, okay. Then we can easily protect the OS code. OS code will be accessed only by the supervisor code which is in the OS code which is running only in the supervisor mode, whereas the user processors may not be able to access that. So MPU has to know which mode the processor is in. Okay, now what are the rules for region? There are several rules that govern the region. Regions can overlap other regions. So I can have a region, so far I was showing you a region is not overlapping with other one. Now suppose I am given a freedom to define a region which are overlapping, okay. So this is the main memory, and there can be a region which are overlapping with each other. These two are one region and this is another region. So there is a overlap. There is a confusion. Now if overlap region is there, how does it behave? I will explain you, then you will understand that. Regions are assigned with priority number that is independent of the privilege assigned to them. So privilege mode is user or privilege mode, okay, but priority number is defined, okay, that is the region number which we are giving. So if the number is higher, then it is higher privilege. So 0 to 7 are the region. So this will be privilege is, priority is higher than this, but privilege is different. Privilege is whether user mode or privilege mode, whether the processor is in which mode, it talks about that. But you can have a region with a higher priority number given to a user process, okay. Similarly, we can have a lower one given to a kernel process, okay, a privileged process. So I will explain you that context, then you will know. When regions overlap, the attributes of region with the highest priority number takes precedence. That means if I will explain you, if a priority number is higher, then that is having a higher precedence. That means what? In the overlapped region, suppose two regions are overlapping, I told you, okay, there are two regions overlapping in this case, okay. Now suppose ARM processor is giving an address which is calling under this region, it will not know whether to take this attribute or can it take this attribute belonging to this. In that case, what happens is, if this region happens to be 3 and this region happens to be 0 priority number, then the attribute belonging to 3 will be considered and taken for this. What I mean by attribute for this means whether what kind of a cache behavior, what is the write buffer is enabled or not, or okay, this kind of different properties of the region are as per this region, because when two regions are overlapping, the region number with the higher priority numbers attributes are considered as long as it is within that region, as long as the memory access is happening within that overlap region. Once it comes here, it will go to this attribute. Once the address access is happening here, this attribute should be used by the processor. So the priority only applies over the address within the overlap region. Okay, some more rules. The region starting address must be multiple of its size. Suppose I will tell you the size is a 4K, okay, kilobyte. The region starting address should also be aligned to 4 kilobytes. That means what? A given an address, 4 kilobyte will occupy how many bits of the address? 12 bits. You can know now by now. Okay. So the address, starting address, okay, has to be mapped, aligned to this size. That means all this will be 0. Now what happens if suppose if it is a 8 kilobyte? One more bit, 13 bits, okay? That also will be 0. That means the starting address is aligned on 8 kilobyte. So, and the size is also very fixed. We cannot be arbitrary sizes. So whatever is the size given, there are fixed number of sizes given in the system, and you can define a region of that size, and then which is aligned on that address. That means that particular address, whatever bits that size occupies, all that will be 0. So that region is starting from that aligned address. Okay. So region sizes are also any power of 2. It has to be any power of 2 and varying from 4 kilobyte to 4 gigabyte. So you should now know the memory, total memory that can be accessed by the processor is 4 gigabyte, correct? 32 bit. So the region can be of maximum size 4 gigabyte. It can be more than that. Okay, you can also define a region which is covering the whole memory area of the processor. Within that, we can define some other smaller regions. Maybe starting with 4 kilobyte. Okay, we can define a region. Maybe this is 8 kilobyte, something like that. You can keep on defining whatever regions you need of only these sizes. Okay, it will 21 values. You can go up to maybe here 1 MB. Then you will start all 2 power 2, right? So you are starting with 4 kilobytes means 2 power 12, correct? Then 2 power 13. Like that you can go on till 2 power 32, which is a 4 gigabyte. So only these sizes are there possible to define in the as a region. You cannot arbitrarily say that 200 kilobyte I want to define. No, you cannot. Okay, this is not a power of 2, and only these kind of numbers which are all given in the book. You can, if you want, or you can find out yourself. It's not a rocket science. Okay, accessing an area of main memory outside of defined region results in an abort. So I have not told you how MPU operates. MPU, what is that MPU doing? Suppose you have configured it and then I defined the system, okay, saying that 0 to 1 gigabyte only is there, okay, in this memory. So I said that okay, all these are all accessible, but beyond this there is nothing, okay, only one region is defined and this is here. Now suppose processor MPU gets an address from the processor which is beyond this 1 GB. The MPU will try to see what are the regions are there defined. So only one region is there, which is assume that it is a region 0. It checks whether this address, which is suppose I am accessing address which is above this, it will see that whether it falls within the defined region in the system. Because I have enabled MPU, so it will be checking for any addresses coming from the processor needs to be within one of the regions defined in the system. Because I have defined only one region of size 1 GB and the address happens to be more than that, something outside this, then it will generate an abort. So far I said that only memory abort, data abort or instruction abort comes from a memory unit. Need not be a memory unit. Memory unit means it could be MPU also, MMU also. Okay. So now you may get more detail about who will give which abort signals to the processor. So the processor will go to the interpreter table and execute all that, whatever we have discussed earlier. All that will happen. So MPU is continuously looking at the addresses. Once it is enabled, it will be looking at addresses going in the what the processor is accessing both for instruction and data, and it will be checking against the region. So it's all done in hardware. That's why I'm telling you it has to be done in hardware, because it is happening every cycle, every m clock cycle. This is happening, the comparison of all the addresses and then try to see whether it is allowed or not. It needs to be done in the single cycle, so you can't do it in software again. It has to be done in hardware, but you configure it using software and then leave it to the MPU to do its job. Okay, I hope this is clear to you. So it could result into a prefetch or data abort. Now, what are the overlapping regions? Why we need it? Okay, I will explain this now. Overlapping regions occur when some portion of the memory space assigned to one region is also in the memory space assigned to another region. I gave an example. So overlapping regions provide us greater flexibility of assigning different access permissions, because you have two regions, so you can give two different access permissions to both of them. But how is it giving you flexibility? Let us see an example. Okay, let me remove all the. Now you have a system with only 256 KB. Okay, see this. These numbers are chosen such a way that they are 2 multiple. Okay, so it's very. You should make even 32 kilobyte is power of 2. So you see the shaded region. The dot shade one is privileged access. That means it's meant for maybe OS code. Why is it given a lower address? That is also there is a purpose. 00 is here. Why is it given 00 or the lower address? Because interpreter tables reside in the lower address here. Okay, there are some configurations possible to keep the IVT interpreter table at the higher address, but I am not talking about it, because if the system has only this much memory, the interpreter table has to be here, and it should be protected. That is why it is having a privileged access, and then the rest of it is having a user access. Okay. Now you see that user access is overlapping with this guy also. That doesn't mean this user process will have a free access to this guy. Okay. Why it will not have? See the number here. Very important. If it was reversed, then what I said just now was possible, but it is chosen very intelligently that region 0 is given to the user processors to access, and then this is a system memory is given a region of 1. So even if a user process is running, the ARM processor will be in a user mode, correct? And it is generating an address to access this location by mistake or intentionally. The MPU will wake up. It's always awake. Okay, MPU will look at, hey, I am getting an address which is overlapping with this region as well as this region. Now, what's the purpose of job of MPU? It should find out who is having a higher priority number. This guy. Then whose attributes it should consider for validating whether this access is valid or not. It should take the attributes of this region, which happens to be a privileged access. Then who is trying to access now? A process which is running in the user space. Then create a abort. Okay, don't allow the access to happen. So the abort handler is implemented by whom? By OS. So it will go and see a user process was trying to access it, so it will not try to fix every problem, and then as I mentioned that during abort handling, it fixes that and executes the same instruction again, right? If that was true for normal access where a page is spoiled or some memory corruption because of some some memory space is not available, or basically it is used for virtual memory where a new page has to be brought into the memory. Those kind of situations, the user data abort has to restart the instruction. Whereas in this kind of cases, if you restart it, it will again encounter an abort because a user process is trying to access the system area. So it will prevent the access and then take appropriate action as per what the OS is programmed to do. So this is what the use of the overlapping region. Here, if you see the region for a region 0, the start and end addresses will be including this particular area. Okay, you may wonder that why I need to do, I could have done it from this region to this. is the user area, right? You are free to do it, but this overlapping I will explain you some more. But if suppose you have mentioned it like this, also there is no reason to get concerned because this will be protected. That's the one of the advantages. The remaining memory is assigned to the user space. Except for this, remaining are allotted. The privilege region 1 is given a higher number because its attributes must take precedence over the user region. So you are intentionally giving a higher number so that its privileges are overruling the privileges of this one. Okay, very good. Now region 1 is not accessible in user mode, though it is overlapping with the region 0. So though it is overlapping, that doesn't mean that this guy can have an access to this region. Okay, this is one of the uses of overlapping regions. Now I'll explain you another one. Take a scenario where this diagram is not showing where the OS is running, okay, or OS code is. Maybe I can keep OS here, okay, everywhere, okay. OS may be there because if tasks are created, there must be some kernel somewhere, so it is doing. Let us worry about that later. Now see what is happening here. This is the gray, white areas are user regions. Okay, it has got user accesses, and there are only two regions: region 0, okay, R0, region 3. Only two regions are defined. Okay, this is the higher priority, higher privilege. Please remember higher privilege, and region 0. Because 3 is a bigger number, right? So it is a higher priority number. See, there is a priority number is higher. That is to a user process. Okay, it is given with a purpose. Okay. Now, since the regions are restricted to either this or only this much area, and region 0 has a total area coming under this purview, it has got an advantage. What is that? Take a scenario where task 1 is running. Okay, it is genuine and it is correct if it generates the address which is within the region. Okay, so will it be allowed? See, region 3 is higher priority compared to region 0. So the attribute assigned to this area is belonging to the region 3 attribute, which says it is a user process and its address range is only this much. That means when the user process is running, this task 1 is running, okay, if it by mistake generates intentionally or whatever to access the area belonging to the other task, what happens? It is not within this region. So even though the region 0 is the lower priority number, because of the restriction in the area, the range of address given to the higher priority number, rest of it becomes inaccessible to this guy. So when task 1 is running, it can only access its own area. Can you get it? It can only access its own area. If it tries to access anything outside, okay, which attribute will become active? This region 0 attribute will become active because region 3 is not covering this region, this area. So region 0 becomes active. What does region 0 say? It's a privileged access. And what is the privilege level of the user process? It is in a user mode. So it doesn't have access to any of this. So the background region indirectly protects the other task areas in the memory. See, what you are seeing is a memory area. Okay, please remember. And in a typical system, in an embedded system in particular, the there is no hard disk associated, and then no the processors are not brought in and go brought out. All those things are not happening. But processors may be switching in the CPU. Okay, processor may be switching. That means P1 will run for some time, P2 will run for some time, and then they may be swapping. But all of them are in the memory. They reside in the memory. Each process is residing in the memory prior to the execution. OS is also residing. So you have to protect when this process is running, we have to protect the other area. And when this process is running, we have to protect the other area. So that is what is achieved by this kind of a overlap or background region. So we call their region this as a background region because that's what is active when a particular task window is open. Okay, even this task is running, this window area is open. When this task is running, only this area is open for its success. Rest of it is protected. Similarly here, so this whole thing is protected, and only this is accessible. So whereas when OS comes, OS gets a control, it will be running in which the mode? It will be running in privileged mode. Then it will have access of whole area. Why? Okay, it will have access for some time. None of the process will be running. Okay, OS only will be running. So this is also not active. So now what happens? This whole thing is accessible. Okay, for the OS, and you can have. Okay, 1 second. Okay, so what we can do is with this background region we will be able to now selectively enable access to a particular region. That's what is the summary. Another useful feature provided by the overlapping region is the background region. Higher priority region is changing a subset of the background region attribute. The higher priority one changing the attribute. So maybe in this scenario, okay, if privileged mode, okay, will not have access to the task area because once you give the access to the, if you are accessing on task area, then immediately that region will become active because it is nothing to do with the process being active in the processor. Once the address comes, that region gets activated. So OS will not be allowed to access this region. Okay, keep in mind. Okay, it may not be needed once the processes are running. There is no need for the OS to or any controller to access them. It is all individually given to the task. That's how it is in this particular scenario. That will be the access restrictions. Okay, correct. Now shields dormant memory areas from unwanted access. What I mean by dormant is if this task is not active, it is dormant. So it has to be protected from other tasks which is running. Region 3 has a higher priority than region 0, even though region 0 has a higher privilege. So region 0 has a higher privilege, whereas region 3 has a higher priority. So any address falling in this category will be controlled by the attributes assigned to this process. And when we say user, the privilege mode can access any region. Okay, only user cannot access the privilege mode. So that way, if you differentiate the accesses to different regions in terms of privileges, then higher privilege can access other part of the memory. So that way, OS also can have an access. So it all depends on how it's implemented. Okay, so in terms of privileges, higher privilege OS will not have an access. The lower privilege region user process will not have access to the higher privilege region. So that's the crux of the matter. Okay, let us quickly see what are the CP15 registers which control the MPU. On system control co-processor is an on-chip co-processor. Okay, so the CP15 I thought I will explain you. So it controls the cache controller, it controls MPU, MMU, it controls write buffer. It also controls instruction prefetch buffer. There is a provision possible that you can have a prefetch buffer in the processor. Before instructions are accessed, that can be residing in a prefetch buffer. Okay. Branch target cache, it will come into play only when branch prediction and other things happening. So let us not bother about that. System configuration signals. Okay, you can in fact in some of the higher processors, high-end processors of ARM family only. I am talking about ARM family. We can even configure the NDNS of the processor in the chip. So you can change the big endian to little endian, need not be coming from the external signal as we saw in ARM 7 TDM. So these kind of configurations of NDNS can also be controlled by the CP15 register. Okay. The control is effected through the reading and writing of CP15 register. Now, how do you read and write? You know that coprocessor instructions are there. The instruction registers are 32 bits long, and then it is access is restricted to only MRC and MCR. So, and only in supervisor mode. So, any of the CP15 instruction can be executed only in the supervisor mode. Okay, and then only these instructions can be executed. See, you cannot give any other coprocessor instruction like use a CDP instruction and then coprocessor transfer instruction. We saw so many other coprocessor instructions which are data processing and transfer instructions. From coprocessor to memory transfer. Those things cannot be done on CP15. Okay, it is implemented such a way that only MCR and MCR and MRC are the coprocessor instruction which transfer from ARM register to coprocessor register and ARM coprocessor register to ARM register. So only these instructions are allowed. That means you can only configure it, and also it has to be in supervisor mode. The processor has to be in supervisor mode if it is executing a CP15 instruction. That means the coprocessor instruction with the coprocessor ID 15. Use of other coprocessor instructions, any attempted access in the user mode will cause undefined exception. So this is the just to recall what you saw earlier when we discussed about coprocessor instruction. So this is the register of ARM which can be put, some value can be put and we can transfer it to a coprocessor register, and the coprocessor registers there are two. Okay, and then you know that there are some operation code. One more operation code is here, additional operation code. So in the CP15 world, this register is called primary register and this is called secondary register. Okay, I will tell you why I am bringing this. This MPU and MMU coprocessors controllers, they maintain two levels of registers and then they associate one register number along, and then some more secondary registers are there. For example, suppose C coprocessor register 0 will have its own secondary register. That means it will have another coprocessor register 0, 1, 2. So they are all secondary registers and this is a primary register. See, effectively there should be a space provided in the controller which is behaving like a coprocessor 15. So when a operand with the CR0 comes, then it will know that any number mentioned here is actually referring to another set of registers in the system. So it can always be built in such a way that when you are writing to a CR0 under CR0 one register, you can always pass two parameters and then try to write into that. So that is what is being done in implementing the MMUs and MPUs as a coprocessor. And COP2 is an instruction. That means it can put some bit patterns here, here, and then instruct the coprocessor to do different jobs. Okay. In our sense, it is a MMU or MPU coprocessor. Okay. Now, there are so many register numbers. These are primary register numbers. Okay. The protection unit has, okay, under CP15, okay, these registers are there. Okay. So if suppose it was a vector floating point processor, its number may be CP10. Okay, that is the normal number given to it. It will have its own registers, right? We saw so many registers in the floating point register. That is resolved by CPID. So it is in a different area, different region. Okay, coprocessor itself has different registers. So CP15 has the primary registers like this. which will be varying from this, and the different purposes, each of them. So they are all given different functionalities. When you write into this, it is controlling the configuration of the system. So that's the way the hardware is designed. This, if you write into something, it controls the cache controller. If you write into this, it controls the buffer, write buffer. Writing into this creates different access permissions for regions, and then you can write into some of the registers here to control the different regions in the system. Okay, region 0 to 7, 8 regions can be there, and there will be different registers for each of them, and you can control their the length and size of the region. So different CP15 registers are allocated. Who has done it? ARM has done it. Okay, because they are all IPs given by the ARM, so they will follow this particular naming convention and the register number. Okay, so CP15 registers that control the MPU are these registers only control the MPU. They are all MPU related. At part of them control the cache also. Some of them are here, some of them control the cache lockdown, which we saw in the previous session. These registers control the cache operation. So this set of registers control only the MPU. Okay, so how do you program the MPU? So if we want to do any region size and location of a region, we have to write into that. I will explain you each of the registers how they are written into. So this I am giving an example here. See, when you are writing this instruction, who is executing this instruction? ARM is executing. This is while programming the MPU, we execute such instructions, and then we say that okay, I am interested in writing into C2, C3, C6, and then the secondary register happens to be this. And then the other opcode is some value I can give 0 or some number, and then from which register in the ARM I am transferring the value. It is R to coprocessor, so I am transferring some value in a particular register in the ARM, whatever value stored, 32-bit value, I am writing into the coprocessor register. Which primary and which secondary registers we can mention. So an MCR instruction, once you give like this, it will be embedded into the coprocessor instruction and then put on the, it will be executed. Okay, when actually this instruction goes on the bus, actually who is executing it? Actually the MPU executes it. Okay, because it will grab it, this instruction, because it will know that it is meant for it itself, CP15, and then it will look at these values and then accordingly it will configure it itself. So actually these instructions are fetched by ARM, and then actually the job is done by the MPU. Okay, it is not that ARM is doing, but ARM has to provide the value. Okay, so when it is this is executed, this instruction is executed, it is transferring the content from RM, whichever register it has mentioned. So ARM has to provide that content out, and this guy will read it. That's all. But and then accordingly it will program it inside. Okay, so you should know how it is done. Otherwise, you will have always the doubt in the back of the mind. Why is secondary register? Why is the primary register? What really happens when you read a book? You may get into all kinds of doubts of how do I understand this. So you should know these instructions are actually accessed from the memory, and it is executed by the processor, ARM processor, and ARM is while writing the code you would have mentioned either R1 or R2, and some proper value would have been written into those registers and then transferred to this. It may be a OS code or you may be writing this code, and then the MPU will grab this instruction because it will see that it is C15 which is meant for me, and then it will read the value from what is coming from R1 while execution happens, this NCR instruction executed, then that value will be taken in by the CPU, coprocessor, and it will configure itself. So then based on whatever instructions we give, it will be done. Okay, I hope this is clear. Once you understand this, the rest of the discussion that I am going to do now will be easier. We should know how MPU is getting programmed. That's what we are trying to understand now. Using these instructions, which are actually registered, ARM registered to coprocessor transfer, and we are writing into the coprocessor, specific coprocessor which are dedicated for some purposes, and it is expecting some parameter to be passed, which coprocessor register, which secondary register, and what operation and which value based on the content of value stored in the register and what register you are mentioned here, it will get configured. Okay, either system control may happen or cache attributes may get returned. So, or you may enable the MPU or anything here, or you may decide the regions. All these things will be happening. Okay, based on this mentioned here. Okay, what is mentioned here? Region and size location can be configured because you need to configure 8 regions. So you need to give a size and length. The starting address and the length of the region you have to mention. So we need at least one big register to hold that values. So a dedicated C0 to C7 8 registers are reserved for different regions in the program. Okay, and which is coming under C6. So under C6 there are multiple registers maintained inside what? Inside the MPU. That you should know where it is maintained. Okay, I hope the whole scenario is clear to you. Okay, so to configure each of the regions, these registers are maintained. So one small example system setup. Okay, let us go by configuring it. Okay, now what are the steps involved in doing it? See, whatever we are given, we are going to do it in this step. Okay, that means we will first decide a region, number of regions in the memory. Okay, how many regions are there and what are their addresses, starting address and the length, all that will be decided by writing into proper registers. Each region 1, 0 to 7, you will write these values, and then we will give different access permissions. Whether a particular region is a read only, this is only read and write, whatever you want. You can give different regions different read accesses or access permissions. Whether user mode or privilege mode, all that will be configured using these registers. Then, if there is a write buffer in the system, whether it can be buffered or not, whether the data when it is written into the memory can go through the write buffer or it needs to directly go to the memory, that we can enable. We will do it using write buffer attributes, and then we will say whether it can be cached or not. Okay, a particular region can be cached, or whether it is an instruction or data cache, and know what kind of a write policy can be applied on the region. All that we will write. After doing all these things, once you decide all the attributes and then you have configured all of them, then only we will come to the system control register. This is the separate register. Under C1 there is a C0. We will enable the MPU. We will enable the cache. All that we will do. Then what happens? The complete system gets done. Now till that point, none of them are enabled because that is the sequence you should follow. You cannot enable it and then start deciding what parameters or what attributes to give. Then there will be a mess. The whole thing will fail. So first decide what each regions are and how they are going to be behaving. What is the behavior we expect? All that we decide based on this writing into this register, and then we at the end we enable the MPU. Till then MPU will not be enabled. That means it won't be active. It won't look at the addresses coming on the bus. It won't even recognize any regions. So you can start filling the values here. Until it is enabled, MPU will be in a dormant state. It will not do anything. Once it becomes active, then it will start controlling it. Okay. So define the size and location first using this register 616. Okay, and then set access permissions for each region using C5. Then please remember it is all under CP15. So everything is inside the coprocessor 15. Inside that the different regions are there. So registers are there. So they may be inside a MPU, or it could be all captured in one place, and then they will be controlling the MPU. Doesn't matter. How does it matter where it is exactly physically located? But we should know that it is access to CP15. And cache and write buffers are accessed using, controlled using this. Okay, and then enable all of them using the C1 register. Now this is how the region is managed. Different regions are there. They have different physical, their different addresses are given, the starting address and size, and you have a priority number. So it will encode the priority and then decide what is the highest priority needs to be enabled, because you have overlapping regions. So If two regions are overlapping, we have to choose the highest priority, and then based on the highest priority, attribute registers will be accessed. Okay, higher priority attributes will be given. Okay, that will decide whether a particular this access, whether it is cacheable or bufferable, or whether user mode or privilege mode access is happening. Now, one thing you should remember here, notice it is only taking the top 20 bits. The bottom 12 bits are not only 20 bits. Okay, this is 20 and this is 12. Oh, sorry, let me clear it. This is 20. Okay, 20 bits are there. Okay, so there is 20 bit is 1 MB. Okay, so the accesses are given with respect to this. Okay, and then the regions are verified. Okay, let me tell you what are the region addresses, and then we will see the details in the next section. Okay, any address generated by ARM is checked against the region it falls under and the attributes associated with that about the highest priority number. Access is allowed based on permissions or about happens. Okay, so in this case we have put 20 because maybe all the regions are 1 MB or more. Okay, if it is a smaller regions, then it would have taken the bits of it also. Okay, very good. Now let us see. Here you can see that. Okay, 12 bits are not used. Only the top 20 bits are okay. This 12 bits. So only the top 20 bits of the address. It could be top 20 bits or less than that. Or we can take always this because this will be 0. Okay, why? You must be knowing it by now. I told you that the sizes of the regions can start from 4 kilobyte to 4 GB. The regions cannot be smaller than this. Okay, and then also the starting address has to be aligned to the region size. Okay, if it is a 4 kilobyte, this is the smallest region you can have in the memory. Then the lower 12 bits of the addresses are addressing this. So since I said that the starting address is aligned to this, it will also be 0, all will be 0. So it is enough if you take only the top 20 bits of the address and store it in the register. That is why you are keeping only these values. Okay, this is actually what I am showing is a CP50 C6 register. Either it could be C0 or up to C7. Okay, based on which region they are trying to program. For example, if you are programming a region for the R0, region 0, then C0 register under C6 of C15 will be used, and its value will be based on what is the region size. If it is a 4 kilobyte starting at 20,000, okay, then top 12 bits will be ignored, and the remaining addresses, this 200 will come here. Okay, now should be 0. This value should be 0, and then this number n is a number varying from 11 to 31. Actually, what it means is 2 power 11 plus 1. So it will become 12 to 2 power 32. So what exactly means? This corresponds to 4 kilobyte size. This corresponds to 4 GB size. So you can choose. That's why it was mentioning that power of 2 only will be given, because you can vary from 2 power 12 to 2 power 13, 2 power 14 up to 2 power 32 can be given as one of the sizes of the region. So we are deciding the size now. That is decided by this 5-bit pattern stored here, which will be interpreted like this. Okay, inside the processor. So once you enable it, this bit you make it set, then this region, whatever address given, will be checked against the size what is mentioned. And if the address whatever being accessed by ARM falls under this region, then it will pick the attributes associated with this region 0, because it is P0. Suppose it will be associated with the region 0. Now you may wonder, where are the attributes of region 0? It is not here. It is only this particular register holds only the region size and location. Okay, so there are some other registers used for that. So I have explained you this. N is varying from 4 KB to 4 GB, and the region size and starting address are determined by the memory map of your system. Okay, so we decide based on the memory map and where you want to use a particular region for what purposes. Okay, access permission. Now that is used by these registers, that okay, C5 and C0. Here you don't need a separate register for each region like what we used for a starting address and the size in the previous case. Now we are trying to set one by one. Region size is done. Now we are trying to get the access permission of each region we want to initialize. That is done by using this register, and this is the bit pattern used for each of them. Okay, the first two bits are used for region 0. This is for region 2, 1, like that. And then what are the number? 0 means region 0 falls under this different values. And then how are we giving it? We are giving different access permissions to it. As I mentioned, supervisor may have a read-write permission for all the regions, whereas user may have a restricted access to some of the regions. Okay. So a typical example could be restricted system resources. You may want no access at all to the user, only for the user supervisor. System configurations, maybe user process wants to know what is the NDNS of the software, whether cache is there or not. Maybe based on that you want to take some decision. So maybe you want some configuration registers to be accessed by the user, but you don't want the user to write into it and then corrupt the configuration. So we only provide read-only permission to that. You can use it. Okay, it's not that you need to provide that permission at all, but you can use this kind of a configuration for a user region wherever they want to access the system configurations. Okay, so you provide only read-only access to the user, but read-write for the supervisor mode. Here we want read-write to both, but that doesn't mean that user can go and write anything into it. So limited part of the supervisor area can be given access to the user because we want some shared system resources. Okay, with the user area. So those kind of things we want to give this kind of a permission. Okay. Okay. See here, user area only is given a user read write, but not user may not have a read write for the supervisor region because it has to be in the supervisor mode for it to do a read write. Otherwise, it is actually both. In this region we have both the supervisor as well as both user also have a read write. So basically, you may give it for the user area where user processor wants to have a access. The system area will be in this region. Okay, we will give this access permission so that this has an access. Maybe some part of it may be read only. OS normally will be here. We don't want user to access at all. Only some shared resources we may give a user access. But for a typical OS code, we will give this region attributes access permission. So what I am trying to say is, suppose you have a region 0, okay, given to the OS area, okay, OS area, then you have to decide which access permission you will give to the OS area. You have to choose this so that user has a no access to it and supervisor has a rewrite access to it. Got it? And you will define the start and end length also. In that case, it will be restricted access. Only OS will have access. Supervisor, user will not have. Whereas if you are the user process area, you may give which one? You may give this because you want to give complete rewrite access for the user data area, this own data area. For a code, maybe you will give user code area. You will give this access because user should not. Even user processor should not write into your own code area. So you may choose read only. So these are the ways you will decide. So cache and write buffer. This is the cache and write buffer behavior for a particular region. So we can decide to do 1 bit for cache. Okay, 1 bit for cache for each region, and then 1 bit for buffer, and then write buffer. So we can decide whether it is a not cached or not buffered, or not cached or buffered, or cached with a write through policy, or cached with a write back policy. So a region of memory can have a different cache properties and a buffering property. So what are the typical scenario? We may give a write this one we may give for a particular, if you want, suppose you want to give a region 0 needs to be configured for this purpose, then you will set both of them to 1. Okay, you will set both of them to 1. Okay, you see this. So thus region 0 will become right step, right back cached. Okay, and if you want to peripheral region, you want to give not cached and not buffered, you will write a 0 in that region. Suppose region 7 is reserved for map to the peripheral area, we may write a 0 here. Okay, that's the way it is configured. Then finally you will enable them. Last process is to enable the region as well as the hardware. So first of all, regions can be there in the system, but it is not enabled. So you saw that E was there. So if it is 0, a region will be defined. Okay, all the parameters will be defined for a region, but it is not enabled at a particular moment, and then you can make it active some other point in time. So the regions can come and go. So that can be done by setting this bit, E bit, okay, of a particular region. That's why I am giving you C0 to C7. Whereas a particular MMU or cache or MPU, this is MPU. So MPU or data cache or instruction cache, if they support two different caches, they will have a different entries here, and they will be set. So then those caches will be enabled. So this is the typical example of how to do it. Okay. Now I will show you a system with a small. No, I am not giving you how to program it, but you have seen all the registers how to write them, so you will be able to achieve this. Okay, you can take it as an example and then try to write into those registers. Okay, to realize this, and it is actually in the book also, this reference book. No, this has got this particular example given, so you can verify it also, or you can go through that particular example to understand it more. Okay, so these regions are chosen like this. Okay, a typical example. This is a protected area where OS related and the stack, lower region IVT intervector table will be there, and then there are active stops regions are there. There is some shared region which are shared by different processors, and then IO devices peripherals are given some different access regions. So region 4, region 3, 2 are the different regions given. Okay, totally there are 4 regions in the system, but it takes care of the complete area of 4 GB. Okay, complete 4 GB is handled. So this will be a typical example. I would like you to go through the book to see how this is all done, so that you have a better understanding of this MPU. Okay, further see another example will make your understanding much more clear. So with this we are coming to an end of the class now. So I hope this was useful. I enjoyed really sharing this complicated information, but I hope you are able to follow them, and see you in the next class. Have a nice day. Bye bye.